Welcome to video lesson 3 on normal strain. Our learning objectives are to define normal strain in one dimension and two dimensions. We will calculate normal strain in axially loaded bars, and we will calculate normal strains in x and y directions for deformed elements. So for this lesson, you should read Beer and Johnston, section 2.1 and 2.5. First of all, let's talk about normal strain in 1D bars. Strain is only a function of deformation in a structure. It has nothing to do with exactly what the loadings were. We would define strain without regard to any of the loadings that would cause it. So we're just interested only in what happened from going from the solid solid to the dash shape. So we're going to define axial or normal strain, normal to this plane of cross section, as epsilon, and that's going to be defined as delta over L. Delta is the extension of the bar, L is the original length. That is what we're also going to refer to later as longitudinal strain for a 1D bar. It's always important to take note of the units of quantities that we're introducing in mechanics materials. So strain is unitless because it has a unit of length divided by a unit of length. So it is unitless or dimensionless. So it would always be inches per inches, meters per meters, centimeters per centimeters, something like that. Now let's talk about normal strain in 2D in multiple dimensions. This is going to tie to section 2.5 in Beer and Johnston. But let's just consider a rectangle that is undergoing deformation. We start out in the original configuration, A, B, C, D, and then this is some small element in a larger structure that's been loaded and the structure deforms, and we now get the shape A prime, B prime, C prime, D prime. Well, we can still define epsilon xx by taking a look at what happens to side AD of the rectangle. So after deformation, we would have AD morph into A prime, B prime. So we would define delta, as we did up here, as the length A prime D prime minus the original length AD divided by the original length AD. So that is also a delta over L. So that equals delta for AD over AD. So much as we defined up here for the 1D axially loaded bar, we have a definition for strain in higher dimensions for 2 or 3 dimensions. If we have a direction that we're interested in calculating normal strain in, and we just take a look at the length of a little line of material in the original configuration and the deformed configuration. Well, I could consider strain in the y direction as well, and that would be the length A prime B prime minus the length AB divided by AB, and that would also be delta AB divided by AB. So it's just the same principle applied to higher dimensions. Now we can talk about some examples. So first of all, let's do an example with normal strain for a 1D axially loaded bar. As we said, it doesn't matter. It's just got a loading of P. We don't know exactly what P is. We don't know what the cross-sectional area of the bar. None of those things matter. So let's find epsilon. So epsilon equals delta over L. That is equal to the deformation given here of 0.12 inches divided by the original length of the bar, which was 12 inches, for a strain of 0.01. Now let's consider a 2D problem where I have strains in the x and y directions. Now let's suppose we have a plate. The plate was loaded in the horizontal and vertical directions. and pulled apart and stretched into it stretched into the dashed configuration from the original solid configuration. Of course, this is not to scale. This is 0.2 centimeters, the extension in the x direction, and this is 0.1 centimeters, the extension in the y direction. So what we'd like to do now is find epsilon xx and epsilon yy. So epsilon xx is 0.002 meters, the 0.2 centimeters, divided by the original length in the x direction, which was 4 meters. That gives us a strain of 0.0005. Epsilon yy would be the normal strain in the y direction, so that would be 0.1 centimeters or 0.001 meters divided by 3 meters or 0.0003 repeating. That's our lesson on normal strain, and that's the end of lesson 3.